Well, it's a pleasure to be here. I understand I only have 10 minutes. I only have 10 slides. And in fact, the objective of what I'm going to be talking about has a lot of similarity with the objective of the previous talk, which is to make access to data easier. But the point of view that I'm taking is that we're familiar with search engines, and a lot of our data is text, or it has metadata, which is text. So are there some ideas for improving search engines? And I'll talk about some particular domains. This is very much research that's in the initial stages, and it doesn't have funding yet, in fact. So my last slide mentions the need for funding, but also we're very interested in applications. So why are we here? Why has data emerged from computer science departments into the general consciousness? Well, a big part of the reason is that there are new types of data, and there are massive amounts of this new type of data. So as we heard earlier from Gabe Doyle, for example, people in linguistics are interested in analyzing Twitter streams, which are huge quantities of data. But fundamentally, a Twitter stream is text. And also, people have very large collections, for example, of videos. But at least if the videos come from television, then a lot of them are labeled with closed captioning, which gives you a summarized idea of the content of the video. And so techniques for dealing with text, so search engines, can be applicable to other types of data also. So I chose this example here of video with closed captioning to illustrate one of the fundamental challenges, which is that these newer sources of text are very noisy. So here it says so-called blue dog Democrats, those physically conservative Democrats. Now, of course, physically is a transcription error for fiscally. But whatever technology we use for searching this had better be robust to that type of issue. 5 minutes, and I'm only on my second slide. Okay. We also have traditional document collections. So this is the interface of Medline PubMed, which incidentally has been around for 60 years now. And for 60 years, they've been indexing with a controlled vocabulary literature from biology and medicine. And I'm sure, actually, PubMed is a great search engine, but there's opportunity for improvement. And if we really think what are the best search engines now, it's the public ones, but I mean Google and Bing. But there's a fundamental reason that some people may not realize why the public search engines are so good. And that's that they don't rely only on analyzing the content of the documents. In fact, even more than the content of the documents, public search engines use machine learning to learn from previous interactions of other searchers with the same content. So I can go to a search engine, I can search for Britney Spears. So I'm completely misspelling her name. But because other people have spelled her name wrong in the past, the search engine behind the scenes has learned that people who search for Britney Spears are likely actually to be interested in Britney Spears. And moreover, the search engine has learned among all the millions of documents out there that mention Britney Spears, which are the ones that are more interesting to people, which are the ones that people click on more. So there's a huge amount of machine learning in public search engines, and we are not going to be able to reproduce that in specialized search engines because we're never going to have the same volume of users. So the challenge is how to improve specialized search engines. And this slide is another example of what a specialized search engine might be. So a few years ago, Toyota had a big public relations and engineering issue with maybe there was unintended acceleration in some of their vehicles. And so they needed to collect a lot of data. And interestingly, the biggest amount of usable, searchable data that they had was text. Because every time the car goes to the dealership, then the service advisor types in very noisy natural language some description of the problem, some description of the resolution. And they have all sorts of documents, and they need a search engine for those documents to be able to try and investigate the problem. So what we've done is build a very preliminary prototype of a topic-based search engine, and we call it SQUID. I'll spare you what the acronym SQUID stands for. So the idea here is that you can have a collection of documents. So here, these documents are small news articles from the 1990s. And you may have a query in mind which you don't know how to formulate it exactly. So I might be interested, for example, in patent litigation, but only in the computer industry and only for cases that have gone to appeal. So I can tell you that information need, but I'm not sure what keywords to use for it, and there are many possible synonyms. So I use the word litigation, but court case or ruling or judgment would all be approximate synonyms. So the idea here is that we want to keep the standard interface, which is sometimes called 10 blue links. You just put in your keywords, and then you get 10 answers, and if you don't like it, you put in a new query. So here, the idea is that you can start with a very vague query like patent, and you'll get your 10 results, and so you can see what's in the collection and whether there are some things that might be interesting. But then each document is labeled with certain topics, and those topics are color-coded here, and you can select the topics that you might be interested in. So here, the user has selected the first topic, the green topic, which is represented by keywords like filed, court, lawsuit, judge, claims. And then that topic has been combined with the original query, and so now the new set of results is only about patent litigation. And then there's another topic, the blue topic. If the user selects the blue topic, then it'll narrow it down to patent litigation in the computer industry. And then if the user selects the red topic, it'll narrow it down further to patent litigation on appeal. And you can see the keywords there, like court, supreme, judge, appeals, and upheld. Yeah. So we have a research challenge here, which is that we need to learn good topics. And I can't go into any of the details, but in fact, we have a topic model which is better than previous methods. And I want to acknowledge Gabe Doyle, who gave a talk this morning, and he was the student who worked on this with me to come up with a better topic model. The other thing that we've worked on even more recently is tagging documents automatically. So going back to Medline, you may not realize the scale of the problem. There are about 1 million new documents per year in Medline, and there are human experts who tag each of these using a controlled vocabulary of 26,000 keywords. And if the human experts spent 10 minutes per document, then with realistic number of hours worked per year, NIH would have to employ 100 staff to do this. And the tagging is always delayed by many months currently. So we're interested in using machine learning to do tagging completely automatically. And we have some preliminary results on this, where our machine learning method does get accuracy which is better than previous machine learning methods, which is better than the automated, semi-automated method currently in use at NIH, which is called MTI. And an interesting finding, we also, we did a separate sub-project where we looked at the consistency of the human experts, because each document is currently labeled only by one human. So we found the tiny fraction, about the 1 in 1,000 documents that have been accidentally labeled by 2 humans, and saw how much those humans agree. And we find that the accuracy of the humans often is pretty low, but the correlation between the human accuracy and the machine accuracy is quite high. So the same documents or the same labels that the software has difficulty making an accurate prediction about, those are the same labels for which the humans actually have difficulty being coherent on. All right, I'll stop here. I already said that funding would be nice, software engineering talent would be nice, and applications would be very welcome. Thank you.
All right, any questions for Charles? We have one up here.
Yeah, I was just wondering what the impact of ICANN's expansion into generic top-level domains may have on ICANN's expansion of generic top-level domains, where they have different like .health or .something like that, how that may impact searching, because they may create customized searchable databases associated with those keywords.
I don't think that's going to have a big impact on public search engines, and I don't think it's going to have a big impact on what we're doing. The public search engines already, they look at the content of the web page, and they look at how other people have interacted with that web page. They don't pay much attention to whether the web page comes from a .com domain really for custom collections of data and documents, often which are not on the internet at all.
Okay, so we have time for one more question, perhaps, and then we should move on. And we also have a 10-minute Q&A at the end of the session, so
Was there another question?
up here.
So I was wondering if you, have the ability to kind of go in the other direction. So build a classifier and combine it with the search engine and basically learn, if you've got a whole bunch of just natural language speech, learn what kinds of things are talked about in context A versus context B versus context C. So kind of use your topic model searching, but without giving it the topic, to learn the different topics.
I think the answer is yes, and to really make the answer interesting, we'd need to talk about a specific application. So the two technologies that I talked about here, one was bottom-up, unsupervised, given a collection of documents, learn what are the topics in that collection, and then whenever you look at a particular document, you can see what are the documents that are prominent, the topics that are prominent in that document, and then if you're interested in that topic, you can then find other documents that also have that topic highly represented. And then the second technology was if you have a predefined controlled vocabulary, like mesh terms in biomedicine, then labeling each document automatically with whether those terms are relevant. And you can certainly combine both of those. So you might use the mesh terms to limit your search to documents that are about diabetes, and then you might look at the topics, and the topics might give you a way of organizing the documents that wasn't anticipated by the people who created the controlled vocabulary. And then, so that would be two different ways of slicing and dicing your collection. And then you could add a third way of slicing and dicing it, maybe, for example, by geography. And you could see, well, what's the pattern of the difference between what people are doing research on in Japan versus what people are doing research on in China? So geography would be a third way of organizing the collection.